Have you ever wondered what actually makes a blockchain tick? What is it beneath all the buzzwords and hype that powers Bitcoin, Ethereum, and the latest wave of decentralized apps? Hi, I'm Lumi Hashley, and in this series, we're breaking down blockchain layer by layer so you can truly understand how this technology works at its core. Whether you're a crypto native or just curious about how Web3 is built, you're in the right place. To kick things off, let's get to the foundation: blockchain architecture. While we often talk about blockchains as if they're single entities, they're actually composed of several moving parts that work together to create a decentralized, secure, and reliable system. At its simplest, a blockchain is a distributed ledger. It's a record of data, often transactions, that's stored across many computers at once. But this ledger isn't just a spreadsheet. It's a complex system that must process, agree on, store, and finalize data in real time. To do all that, every blockchain relies on four core functions: execution, consensus, data availability, and settlement. Execution is the function that processes transactions. It runs the code, updates the state, and ensures that when you send a token or interact with a smart contract, those changes happen as expected. Consensus is how all the participants in the network come to agreement. Whether it's Bitcoin miners using proof of work or validators staking on a proof of stake chain, consensus ensures that everyone accepts the same version of history. Data availability means making the contents of each block accessible to the entire network. Without it, no one could verify that the information being processed is accurate. And settlement is the final piece. It ensures that once a transaction is confirmed, it becomes permanent. Settlement gives blockchain its power of finality. It's what makes tampering nearly impossible. Now that we've laid out the basics, let's put this in context. When Satoshi Nakamoto introduced Bitcoin in 2009, it was a monolithic chain. That means all four of those functions: execution, consensus, data availability, and settlement were handled in the same place, on the same layer. This made Bitcoin secure and reliable. But it also meant that as more people used the network, it became slower and more expensive to operate. Ethereum followed a similar model. And while it introduced smart contracts and an entire developer ecosystem, it still struggled with scale. That's where the architecture conversation began to evolve, from monolithic design to modular alternatives. But before we get ahead of ourselves, we need to dive deeper into monolithic blockchains. Many of today's leading platforms, including Solana and Bitcoin, are still designed this way. Understanding their strengths and limitations is key to understanding where blockchain is headed next. In Chapter 2, we'll take a closer look at monolithic blockchain architecture. We'll explore how these systems operate, why they're still widely used, and what makes them both powerful and constrained. Let's dive in. Now that we've laid the groundwork, let's get into one of the most fundamental design choices in blockchain development: monolithic architecture. So, what exactly is a monolithic blockchain? In short, a monolithic blockchain is a system where all the core blockchain functions, execution, consensus, settlement, and data availability, are handled within a single, unified layer. That means every node in the network processes transactions, reaches consensus, stores the data, and finalizes it, all in one place. This model is the original blueprint. It's how Bitcoin was built and how Ethereum started. Everything happens in the same environment by the same network of participants, making the design relatively straightforward and easy to reason about. One of the biggest strengths of monolithic architecture is its simplicity. Because everything is handled by a unified set of nodes, coordination overhead is low. The trust assumptions are minimal, the design patterns are well understood, and security is tightly coupled with the chain's consensus mechanism. In a monolithic system, when a block is finalized, it's truly final. There's no waiting for cross-layer confirmations or dependencies. This approach also creates predictability. Developers know exactly what environment their smart contracts will run in, and users benefit from the security guarantees that come from tightly integrated consensus and execution. But as with most things in crypto, there's a trade-off. Monolithic blockchains tend to struggle with scalability. Because every node must process every transaction and store all the data, the system becomes increasingly bloated as adoption grows. This is often referred to as state bloat, and it's a major concern for long-term sustainability. Resource requirements also rise sharply. Running a full node on a monolithic chain can become prohibitively expensive, leading to centralization pressure as only a few well-resourced participants can keep up. And then there's performance. As networks scale, latency increases and throughput becomes limited. Even with clever optimizations, it's hard for a single-layer system to scale linearly with demand. This is the core issue that drove Ethereum's transition away from its original monolithic design. Let's look at some real examples. Bitcoin is the classic monolithic chain. It processes basic transactions, reaches consensus through proof of work, and offers rock-solid security, but its throughput is extremely limited. Ethereum 1.0 expanded that model with smart contracts, but hit similar bottlenecks. Gas fees surged during periods of high demand, and block space became a premium commodity. Solana, on the other hand, took a different route. It's a modern monolithic chain built for high performance. Through aggressive optimizations like proof of history and parallel execution, Solana has pushed the boundaries of what's possible in a monolithic architecture. But even Solana has faced growing pains when it comes to network stability and decentralization trade-offs. So the big question is, how do we keep the strengths of monolithic design, such as security, finality, and simplicity, while solving the scalability problem? This is where the modular blockchain revolution begins. In the next chapter, we'll explore how a new generation of blockchain projects is breaking the architecture into pieces and assigning each function to a dedicated layer. It's a bold new paradigm that promises greater flexibility, scalability, and innovation. But modularity comes with its own set of challenges. So let's unpack that next. All right, contrarians, now that we've dissected the strengths and limitations of monolithic blockchains, let's talk about the shift that's shaking up the entire blockchain design space. Welcome to the age of modular blockchains. To understand where this revolution is coming from, we need to zoom out and look at how complex systems evolve. In technology, modularity is a well-worn strategy, from early computing to modern cloud infrastructure. Breaking a system into independent, specialized components has always been key to scaling performance and innovation. That same principle is now being applied to blockchains. A modular blockchain separates its core responsibilities into distinct layers. Instead of having a single chain handle execution, settlement, consensus, and data availability all at once, modular systems assign each of those functions to purpose-built components. Let's break those down quickly. Execution is where transactions are processed and smart contracts run. Consensus ensures that the network agrees on the current state. Data availability ensures that transaction data is publicly accessible and verifiable. And settlement is where finality is established and cross-layer security is enforced. In monolithic chains, all of these happen in the same place. In modular chains, they're distributed across specialized layers, allowing each to scale and evolve independently. The result, a much more flexible and scalable design. Execution layers can be optimized for speed, while consensus layers can focus on security. Developers can choose components that best suit their use case, and new layers can be introduced without overhauling the entire system. The most well-known example of this shift is Ethereum's own evolution. Ethereum started as a monolithic chain, but is now gradually transforming into a modular one. Execution is moving off-chain through rollups, while Ethereum focuses on providing settlement and consensus. Eventually, it will rely on external data availability layers too. And that brings us to Celestia, a project that was built from the ground up as a modular blockchain. Celestia doesn't process smart contracts or transactions. Instead, it provides a data availability layer that other chains and rollups can plug into. Think of it as the internet's bulletin board for blockchain data. It doesn't care what you build on top of it. It just guarantees that your data will be available and verifiable. Polygon Avail takes a similar approach, specializing in scalable and secure data availability. It gives rollups and application-specific chains a reliable foundation to store and retrieve their transaction data. This modular approach is incredibly powerful, but it also introduces new complexities. Now you need to coordinate between multiple layers. You need protocols to bridge execution with consensus, to verify data across chains, and to ensure everything settles correctly. With great flexibility comes great responsibility. Still, the modular vision is compelling. It allows blockchain systems to scale like the internet did, by layering, specializing, and decoupling where necessary. But here's the twist. Most modular systems still need a high-performance execution layer to actually run user applications. And that's where rollups come in. In the next chapter, we'll explore rollups, the engines powering the modular future. Whether you're bullish on ZK, optimistic about optimistic rollups, or just trying to make sense of this fast-changing space, you won't want to miss what's coming next. Before we dive into rollups and how they're fueling the next stage of modular blockchain scaling, let me ask you for a quick favor. If you're enjoying this deep dive, make sure to give this video a like and subscribe to the channel. It really helps us reach more contrarians like you. And if anything sparks a question or a hot take, drop it in the comments. I read every one of them. All right, now let's keep going. Let's take everything we've learned about modular blockchains and zoom into the beating heart of their scaling capabilities: rollups. If modular chains are a multi-layered cake, rollups are the rich execution layer that brings the flavor, batching transactions at scale without compromising decentralization. So, what exactly is a rollup? At its core, a rollup is a scaling solution that executes transactions off-chain, then posts data or proof of those transactions back to a base chain. The result is more throughput, lower fees, and better efficiency, all while relying on the security of a main chain like Ethereum. Think of it like bundling hundreds of letters into one package instead of mailing each one individually. Rollups come in two major flavors: optimistic and zero knowledge. Let's start with optimistic rollups. These systems assume that all transactions are valid by default. Anyone can challenge a fraudulent transaction during a specific dispute window using what's called a fraud proof. If someone successfully proves that fraud occurred, the invalid transaction is reversed. This model is simpler to implement and has lower computational requirements, which is why networks like Arbitrum, Optimism, and Base have become the poster children of optimistic rollups. But there's a catch. Withdrawals from these rollups back to Ethereum typically take about 7 days to finalize, which isn't ideal for users needing fast liquidity. Now, on the other side of the spectrum, we have ZK rollups. These use zero-knowledge proofs to validate each batch of transactions before posting them on-chain. In other words, the system proves that everything is correct from the start, eliminating the need for a dispute window. That makes finality much faster and security arguably tighter. ZK rollups are more complex to build, but they've come a long way. zkSync Starknet and Polygon ZK EVM are leading this frontier, pushing the boundaries of what's possible with cryptographic efficiency. Of course, each type comes with its own trade-offs. Optimistic rollups offer simplicity and broader developer adoption right now, while ZK rollups are more elegant in theory, but still maturing in practice. However, both share the same core value. They serve as powerful execution environments that plug into modular blockchains, allowing them to scale without compromising security or decentralization. And here's where it all clicks. Rollups interact seamlessly with settlement layers like Ethereum and with data availability layers like Celestia or Polygon Avail. This architecture splits the workload, enabling rollups to focus purely on executing transactions, while other layers take care of consensus and data storage. The result is a more efficient, scalable, and user-friendly blockchain ecosystem. We're already seeing the impact of this architecture in the wild. Arbitrum consistently handles more daily transactions than Ethereum itself, often at a fraction of the cost. zkSync has shown remarkable potential in onboarding developers through its native account abstraction features. And Polygon ZK EVM is gaining traction in real-world enterprise use cases thanks to its fast finality and strong Ethereum compatibility. Rollups aren't just a theoretical upgrade, they are actively reshaping how developers build and how users interact with the blockchain. It's a new design philosophy, one that aligns with the core values of decentralization, while solving the pain points of speed and scalability that have long haunted Web3. So now that we've got a solid understanding of rollups and their role in modular architecture, the next logical question is, how does all of this translate into real-world applications? In the next chapter, we'll explore how both monolithic and modular blockchains are used in practice, from financial systems to gaming platforms and NFT ecosystems. We'll look at which architectures excel in which scenarios and what that means for the future of decentralized applications. Let's keep going. Now that we've dissected the theory behind blockchain architecture, let's bring it all down to earth. Because when all is said and done, what really matters is how these architectures perform in the wild. What kinds of apps do they power? Where do they shine? And where do they stumble? Let's start with monolithic blockchains. These are your all-in-one platforms like Bitcoin and Solana. They handle everything: execution, consensus, data availability, and settlement, all in a single layer. That kind of vertical integration has its perks. For example, Solana's blazing speed and low fees make it a natural fit for high-frequency trading apps and consumer-facing platforms like NFT marketplaces. Because everything lives on the same layer, transactions finalize quickly, and applications enjoy predictable performance. Gaming platforms have found a sweet spot here too. Star Atlas and other immersive experiences built on Solana benefit from the consistent latency and throughput that monolithic chains offer. In these kinds of real-time environments, splitting up core functions across layers could introduce delays that ruin the user experience. So, when performance is critical and the ecosystem is tightly bound, monolithic works. But as Web3 scales, we're seeing modular blockchains rise to meet the moment. Take Ethereum, for instance. Once a monolithic smart contract platform, it's evolving into a modular hub through its embrace of rollups. Arbitrum, Optimism, Base, and zk Sync are now handling a growing share of Ethereum's daily activity. This shift unlocks massive scalability without needing to overhaul the base layer. It also gives developers more choice. You want low fees? Pick a rollup optimized for throughput? Need stronger privacy? Build on a rollup designed for confidential transactions. Celestia is another standout in the modular world. It specializes in data availability and lets developers build their own execution environments, essentially custom rollups, on top. This is powerful for startups and experimental projects that need flexibility and don't want to build everything from scratch. Polygon Avail is following a similar path, providing fast, verifiable data availability to rollups and app chains. These modular providers act as foundational layers for entire ecosystems. They're less about hosting the apps themselves and more about empowering other builders to innovate without compromise. So, how do these models compare in practice? For users, monolithic chains often offer faster onboarding. Wallets, tokens, and apps are tightly integrated, so everything just works. But they can struggle with congestion and high fees under load, especially when adoption scales faster than performance. Modular chains, on the other hand, spread that load out. By specializing and outsourcing certain functions to different layers, they allow each part of the stack to scale independently. That leads to better long-term performance, though it can come with a learning curve for developers and more fragmented tooling. Economically, monolithic chains can feel more efficient at first, but modular platforms often offer better cost efficiency in the long run. Developers only pay for the functions they need, and scaling strategies can be fine-tuned. That's a big win for Web3 startups watching every gas fee. Security also plays out differently. In monolithic chains, security is tightly coupled across functions. If you trust the chain, you trust the whole stack. With modular architectures, trust is distributed. That means stronger customization, but also a greater need for audits and coordination between layers. Both approaches have their place. In fact, we're starting to see them converge in creative ways. Hybrid models that combine the best of both worlds. And that brings us to the final chapter. What does the future of blockchain architecture look like? Are we heading toward modular dominance, or will new innovations breathe fresh life into monolithic designs? So far, we've looked at how blockchains are built and how they function today. But what happens next? What does the future hold for blockchain architecture? One thing is becoming increasingly clear. The future isn't a binary between modular and monolithic. It's a spectrum. And we're heading straight into the age of hybrid design. Projects like Ethereum are leading the charge here. After years of operating as a monolithic smart contract platform, Ethereum is now evolving into a modular network with rollups handling execution, dank sharding advancing data availability, and a renewed focus on settlement layer efficiency. But it's not abandoning its roots. Instead, Ethereum's roadmap suggests a blend, optimizing its base layer while letting external layers innovate freely. Celestia, on the other hand, was modular from day one. It was built to be the backbone for other chains, offering data availability as a service. Now we're seeing chains launch directly on top of Celestia, creating ecosystems where modularity is native and fully embraced. It's no longer an idea, it's happening. But even modular systems are borrowing from monolithic design. Rollups like zk Sync and Starknet are pushing execution capabilities to their limits. Some are even experimenting with features that give them more independence from Ethereum's mainnet. It's a kind of architectural remix, where modular chains build in monolithic traits to enhance performance or control. Looking beyond software, hardware innovation is also reshaping what's possible. As blockchain nodes get faster and more efficient, some of the trade-offs that once made monolithic designs difficult to scale may soften. With better compression, parallelism, and cryptographic advancements like recursive proofs or zero-knowledge succinctness, blockchains may do more with less. That could blur the lines between modular and monolithic even further. Of course, there are still major challenges ahead. Interoperability remains a huge pain point. If modular ecosystems are going to thrive, we need secure bridges and shared standards that let chains talk to each other seamlessly. Otherwise, we just end up with new silos. Security also needs to evolve. As trust gets distributed across layers, execution here, data there, consensus somewhere else, it's vital that we understand the risks, validate assumptions, and constantly push for better tooling and audits. So what can we expect over the next 5 years? We'll likely see more modular chains enter the scene, each with sharper specialization. Execution layers built for AI, rollups tailored for DeFi, and data availability providers racing for efficiency. But at the same time, monolithic chains will refine their models, adopting some modular ideas without losing their simplicity. Ultimately, blockchain architecture is following a path we've seen in other parts of technology. First, systems are built as tightly integrated machines. Then they unbundle, specialize, scale. And finally, they converge into networks that are smarter, more flexible, and more powerful than before. That's where we're headed. If you found this series helpful, don't forget to like the video, subscribe to the channel, and share it with anyone who's trying to wrap their head around the future of Web3 infrastructure. Got questions or thoughts? Drop them in the comments. I always love reading your takes. And until next time, stay curious, stay critical, and most importantly, stay decentralized.